I did put the math boot camp in the graphic now.
Is that what that June 23rd thing is?
Yeah.
Oh, nice. Math Thursday, but we're Numworks too, are we?
Yeah, we did four.
Oh, I was thinking we had. I mean, I'm still gonna use it.
Yeah.
I'm still gonna use it.
Well, we're not
but...
being sponsored by Numworks.
Got it. So the sponsorship is open.
We're sponsoring ourselves.
Expo markers. Come at me.
The big ones are supposed to be great.
Ooh. Bic dry erase markers. Yeah. Do you guys have any recommended dry erase markers that you got? I'll take them. All right. Welcome to Math Thursday. Here we are, where we go through. I have been a math and science teacher for 20 years. And so we are here to answer your questions, whatever you've got going. Pop them in the chat. Send me a message. I can answer. So mainly we were focusing on pre-algebra through algebra 2, a little bit of pre-calc, things like that. So yeah, if you have any questions, if you're getting ready for a final, you're kind of panicking, maybe you're not into finals yet and you're just kind of like taking a test or something like that, or you're just curious about something that you saw on TikTok or wherever, just let me know. You can put it in the chat. You can send me a message. We have lots of things that are going on the channel. So make sure you click the link and do the stuff. So sign up for notifications and all of that kind of stuff. We've got a Getting Ready for Algebra 1 boot camp going on this summer where you can join me for an hour virtually once a week for about 6 weeks. And we will go over some of the major topics that are big, like holdovers from pre-algebra and really essential pieces to understand before we can go into Algebra 1. So join me, click the link, do the stuff, all those good things. All right. So let's get into it. Let's start off with just a simple proportion. Okay, so we're going to start off with just x minus 4 over 10. Actually, hold on. Here's what I can do. I'm going to go ahead and let's see. Okay, actually, yeah, I guess so. We'll do a little. Just trying to pull up some of my problems that I've done or that I've put up for some things. Okay, so let's start off with an equation. So we've got -4 times -3x plus 3 equals 84. Okay, so let's start off with this. So once you have an idea what the value of x is that's going to make this true, put it in the chat. Let's see if you're right. We got 8, we got 6. Let's see. Finding the volume given the area. Henry, can you give me a little more information about that? Finding the volume given the area, given the surface area of a solid, I'm assuming? All right, let's. Oh, how do we get anything but 8? All right, let's see. So this is -4, and we've got -3x plus 3. Okay. All right. So with this problem, we actually have a choice of how to start it. So we could multiply, we could distribute this -4 all the way through, or without distributing, we could actually divide both sides by -4 first. Because these two things are being multiplied here, right? This -4 is being multiplied by -3x plus 3. So I'm actually going to go through, I'm going to divide -4 on both sides. So now this -4 goes away. So I've got -3x plus 3. And now that there's nothing that's kind of being multiplied by this, I can drop the parentheses. Okay, 84 divided by -4 is going to be -21. Okay. So now I subtract 3. Subtract 3. That's going to go away. I've got -3x equals -24. Then I divide -3, divide -3, and I've got x equals 8. Interesting. All right, so we've got 8 here. So let's see, how do we get 6? Let's see. So 6, I wonder if we distribute, maybe when you if you distribute this -4, remembering that this would become a positive 12x and this would become a minus 12. So sometimes if you get the negatives mixed up, that can really kind of separate things, right? That can give you a lot of things. Okay, so do linear equals solving for x. Michael, I'm not sure what that is all about. So what grade math is this equation? So this equation is probably something that you're first going to be really exposed to in Algebra 1, which may be like 8th or 9th grade, maybe 7th grade for some schools. So this is a really solid Algebra 1 problem, but this is something that I would still revisit with my Algebra 2, with my trig, with my, even into pre-calc, revisiting, just kind of solving these basic linear equations because it shows up so frequently in any math class that you're working on in high school, right? Okay, so let's see. So linear equation solving for x. So Michael, this is a linear equation solving for x. So I'm not sure what else you need here. Okay, so I see unit circle a lot. Okay. All right, so unit circle, we've got linear equations. Oh man, Snoop, trig is so fun, but trig, when I was in high school, really kind of threw me for a loop. But trig is pretty fun. But we're gonna do some of the unit circle right now. So, and we can do some trig stuff too. So I'm seeing rationals, I'm seeing factoring. Let's see, okay, so rationals, do you mean radicals? All right, so standard deviation, Brokey, I can't read your name, I'm sorry. So standard deviation, are you able to use a calculator? If you're able to use a calculator, you can just kind of use your calculator to do that for it. Okay, so standard deviation, there's really just a formula. If you have a TI-84 or something like that, you've got that. Okay, so I'm seeing SOHCAHTOA and unit circle. Let's start there. SOHCAHTOA and unit circle. Okay. So those are the two that I'm going to get to right now. And that'll be some basic trig problems. Okay. All right. So SOHCAHTOA. All right. So what trig is? Trig is based on the connection between the angles and side lengths of a triangle. So when you're looking at a triangle, usually you really start with right triangles because it is sort of all based off of that. So when you're looking at these triangles, right? You name a triangle for all of the angles that are at the vertices, right? So these are all with uppercase letters, and then the side length that's across from angle A would be side A, but you use a lowercase letter. So you use lowercase letters for sides, and you use uppercase letters for vertices or for the angles. Okay, so trig is what joins them together. Now, what's neat about right triangles is all sides in a right triangle are going to fit in with the Pythagorean theorem, right? That's the relationship between those sides, always, right? A squared plus B squared equals C squared. I've kind of misnamed it, but as you guys know, those of you who have been here for a while, I don't really like saying A squared plus B squared equals C squared because for this reason right here is that A squared plus B squared is not going to be C squared in this case. What's always true is that if you take the leg squared plus the leg squared, that's going to give you the hypotenuse squared. So just memorizing A squared plus B squared equals C squared, like while it is useful, what you really want to do is the legs squared and adding those together and then the hypotenuse squared. Okay, so that's what I always encourage my students to do is think about it, not just don't get stuck on the letters because the letters can actually be anything. Okay. All right, so with the Pythagorean theorem, again, so you're always going to have that relationship. Now, what also is always going to be the same relationship in right triangles is the angle to the side length. So the way that the angles are, that's also going to determine the side lengths, what they are. So there is only one right triangle that has a certain set of side lengths. Okay, and it's going to have the same angle measures as well. So it's always going to be exactly the same. Okay, now that the relationship between the side lengths and the angles, that is what trigonometry is. So trigonometry or trig is where you're studying you're using the angles and the side lengths together to solve triangles, to solve problems, to solve all these different things. Okay. So when we're talking about trig, we have to have a way of, or we kind of need to set like a focus angle, like an angle that we're going to focus on, right? And what we're going to do is we're going to set that as this Greek letter, which it looks like an O with a line through the middle, and that's called theta. Okay, so theta is sort of how we mark our angle of interest, or like what angle we're focusing on. So in this case, theta is the same thing as angle A. So once we set this theta, okay, I'm going to erase these side lengths because we actually have special names for these in relation to that theta. So these names of the sides are, we've still got legs, we've still got hypotenuse, right? In fact, this is always going to be the hypotenuse, no matter what. Okay, that side that's across from the 90-degree angle will always be the longest side. It will always be called the hypotenuse. Always, always, always. Once we set our theta here, though, we have different names to like distinguish our legs, right? These are our legs that make the right angle. So the side length that's right opposite from the theta, right across from the theta, we call that the opposite. Okay, so I'm just gonna write OPP. Yeah, you know me. Okay, so we're gonna do the OPP, that's the opposite. Okay. And then this leg here that is directly connected to theta, it's one that actually makes that theta angle. We call that the adjacent. I'm just going to do ADJ. Oh, it ties way back. Yeah, it's a lot of geometry. Yeah, but it's where geometry and algebra really meet. I mean, there is a lot of overlap, which is why we actually at my school started doing an integrated math approach, because there's so much overlap between algebra and geometry. Now, if my theta were up here, this would be called my opposite and this would be my adjacent. This would still be my hypotenuse, but the theta can change, and this opposite and adjacent are just in relation to theta. So now the trig ratios. Okay. Depending on what my theta value is, it's going to have a set ratio of the side lengths. And we have special names for these ratios between the different sides. So if we are talking about the ratio between the opposite and the hypotenuse, we call that one sine, which is S-I-N. Okay? It's on your calculator, so you may have seen it. You've probably seen it, and you're like, why does it say sin? So sine theta is the relationship between the opposite over the hypotenuse. So sine theta is the opposite over the hypotenuse. Any angle that you have has a specific opposite over hypotenuse. It's always going to be the same ratio. Okay, so if I have this angle for my theta, that opposite and that hypotenuse will have a specific ratio. Okay, and you can see what that ratio is, right? If you go onto your calculator and you do, okay, sine of 60, okay? Sine of 60 is the square root of 3 over 2, which is 0.866. It's always going to be that, okay? Sine of 30 is 1/2. So the sine of 30, if this angle is 30 degrees, this side length here is going to be half of this side length here. Always, 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 always. I love it in math when you can say things like always. It's great, okay? Sine of, let's get away from the special right triangles, and maybe sine of, I don't know, 48 degrees is 0.743144. Now, I don't know what those side lengths are going to be, but I can use that ratio because if I know my angle and I know one of my side lengths, I can figure out the other side length using trig, okay? So, Toa. So if we talk about the theta and we're looking at the ratio between the adjacent and the hypotenuse, that one is cosine theta. So cosine theta is the adjacent over the hypotenuse. So it's the ratio between the adjacent and the hypotenuse. Oh, Cody, I do like that. I do like that. So instead of SOHCAHTOA, you do, oh heck, another hour. And then the last one is of algebra. So the ratio between your opposite and your adjacent is called tan or tangent theta. I like that. So if you hear about SOHCAHTOA, which I mean you can see on my notes right here, I wrote it down, SOHCAHTOA. Okay, so SOHCAHTOA will get you through almost every problem in trig. But its sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Same thing, right? So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So like I said, if you were given any of these values, you could find another one, right? So yeah, cosecant, cotangent, and secant, those are the other three trig ratios. So cosecant is you flip this, it's hypotenuse over opposite. Secant is hypotenuse over adjacent. Cotangent is adjacent over opposite. I just kind of introduce my students to that. And then beyond that, I mean, you're really not working very frequently with anything other than these big three. So especially in like an Algebra 2 class, when you're just learning it, like there's no real need to emphasize like secant, cosecant, and cotangent. Like they're more ratios, and sometimes they can make calculations a little bit simpler, but I don't know. You pick your battles. So I picked to just stick with the with the big three here. And that seems to be okay. So if you're given any of this information, right, you can even use these relationships to figure out what the theta value is. So what the angle is based on these side lengths. You can plug in what you know and solve for what you don't know. There's a hand trick I know for the unit circle, but I don't know about the hand trick for the right triangle trig, for the SOHCAHTOA stuff. I'm not sure what that is. Abs, you're not cooked. Okay. All right, so with this, okay, let me see. All right, so guys, for those of you who are just joining us, I'm Sarah. Welcome. I've been a math and science teacher for over 20 years. So if you have any questions, we primarily focus pre-algebra through like algebra 2, maybe a little bit of pre-calc, but our main focus is really like algebra 1, algebra 2. But if you have any questions, even if they are about pre-calc or even into calculus, put them in the chat because we've got a great supportive, loving community here, and if you need any help on things, anybody who can help will certainly jump in and let you know. But we also have a Getting Ready for Algebra 1 boot camp going on this summer, where every week we'll revisit some topics in pre-algebra, and we will preview some topics in Algebra 1 that I know are going to get you just that really solid foundation. So if you're a student going into Algebra 1, or maybe you're a teacher teaching Algebra 1 for the first time, or maybe you're a parent and you're nervous about your own kid going into Algebra 1 and you want to brush up on your skills, let's do it. In-person tutoring. So, D-Day, if you're in Michigan, send me a message. But so in-person tutoring would just be local here, but send me a message. Maybe we're nearby. I do help with geometry. Can you do math values with these formulas? I do teach geometry. Yes. So if you have a geometry problem, let me know. Okay. So some of the problems that you might do with this is, if you were given, maybe you're given a triangle like this, here's the right angle, and let's say my theta is up here. Okay. We'll say that this side is 5 and this side is 7. Okay. So what I have here, actually, you know what? I'm going to change that. Let's just do a 3, 4, 5 triangle. So this side is 3, this side is 4, this side is 5. This is what's called a Pythagorean triple, which is where all 3 sides are integers. You've got 3, 4, and 5. They're all rational numbers. It's really nice to work with these. And these you can actually double. Like you could do 6, 8, 10. You could do 12, 16. What did I do? 20. But these 3, 4, 5 triangles, and there's a few of them. There's a few different ones. So if I were to do, Tony, I will do the unit circle. It is next on my list. I'm just going to do another one like this, and then we'll get into that. So if I were trying to find, sine theta, so sine is my opposite over my hypotenuse. This is my opposite, is 4, and this is my hypotenuse. So remember that the opposite is always across from theta. Now, even though on my diagram my opposite was over here, I changed where my theta is. So remember, the theta, the opposite and the adjacent are relative to theta. Okay, so sine of this theta is 4 over 5. And you can do that all the way around. You can just kind of plug those in and do 4 over 5. So cosine would be 3 over 5 and tangent would be 4 over 3. What you can also do is I can figure out what this angle is. Now what's fun is that in this Pythagorean triple, this theta, if you see a 3, 4, 5, it's always going to be the same thing. It's always going to be that specific angle because there are only 2 specific angles that we'll calculate in just a second that give you that 3, 4, 5 triangle. And those angles are going to be the same even if you double this, even if this were a 6, 8, 10. Because if I double all my side lengths, that's making it into a similar figure, and similar figures have proportional sides and identical congruent angles. Pretty cool. So to figure out what our theta is, I need to do something called arc sine or inverse sine, just kind of inverse trig, which is where we go, we have theta equals sine -1, and then we use our ratio here, 4/5. Now that sine -1, if you have, well, any graphing calculator that you have or any calculator that you have, oh, let me fix my settings on this to turn it down a little bit. I know it's not ideal, but that's a little bit better. Okay, so any graphing calculator that you might have, you're going to, if you have like a shift key or a second or something like that, whatever it's called, right? If you look right above the sine, cosine, and tangent, there will be this symbol, this sine -1, or like mine is A sine, A cosine, A tangent, because that's arc sine, arc cosine, arc tangent. So I'm going to do shift arc sine of 4/5. And I get 53.1301035. Now I know it goes on and on and on. So I'm going to call my theta, usually with, when you're figuring out angles, you round it to the nearest whole degree. So I'm going to call this theta 53 degrees. Okay. So that means that in a 3, 4, 5 triangle, this angle that's opposite from the 4 side, from the medium side, is 53 degrees. Again, it doesn't matter how big this triangle is. If it's a 3, 4, 5 ratio or 3, 4, 5 triangle, the ratio of the sides is always going to be the same, which means the angle measures are always going to be the same. There you go. Okay, so unit circle. Okay. Oh yeah, this is so much. This is I enjoyed math when I was in high school, but I think that's a pretty common thing, is like people revisiting it back as adults. I mean, there's a lot of times, like there's a lot of brain research and brain science that goes into it, that like your brains as teenagers are just not ready to learn some stuff. Now that's, you know, I know it's broad strokes, blah, 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 right? But overall, the brain science suggests that like sometimes, and a lot of you may have found this, a lot of my students have found this, where it's like, oh my God, my teacher tried to teach me that in 7th grade and I just had no idea what she was talking about. And then now as a junior or senior, that makes so much more sense, right? Because your brain just can make sense out of it, because your brain is ready to make those connections and grow those sulky and all of that kind of stuff, right? So, you know, if you don't get it first pass, like don't beat yourself up. It's okay. It's okay to not get it, right? It's okay to not understand, but it's not okay to not try, right? You've got to try, right? I always give my students I try to give my students like processing time, right? Like just look at a problem and look at the answer and just see what you can pick up on, right? So much of math is just patterns and recognizing patterns. And so, you know, sometimes you can pick up on the pattern, sometimes you can't, and that's okay. But at least you're trying, right? Try to pick up on the pattern. Okay. All right. Yeah, polar integrals. Ooh, any integrals. Blech. Okay. All right, so unit circle. All right, so the unit circle, I'm going to give kind of a sort of a brief intro to the unit circle. So the unit circle is based off of those, based off of special right triangles, and based off of special right triangles, and based off of trig ratios. Okay, so the unit circle is a circle, right? And the unit circle is looking at, it's a circle with a radius of 1. Okay. So it's we use it in trig to be able to find these specific values and these exact values of like ratios and trig ratios and things like that. So it goes all the way around kind of like this. Ugh, that one went all goofy. Okay, so you're going to have like 3 lines in each of these. And these are really just marking 30, 45, and 60 degrees. And I know this is obviously not to scale or anything like that. Each of these points here is where it intersects with that unit circle. So the distance here from the center to the circle is going to be 1. Okay, that radius is 1 all the way around. Okay. Now what I'm going to do here is I'm just going to focus on the first quadrant. Okay, so I'm just going to focus on the first quadrant because really it repeats itself all the way around. Now there's negatives and there's positives, right? But I'm just going to focus on this. So you have 30 degrees, you have 45 degrees, 30 degrees, 45 degrees, and 60 degrees. Okay. So this is a 45-degree angle here to this line. This point here, okay, now if you want to look at a unit circle while I'm kind of going through this, like literally just Google unit circle and find a PDF of it. And it's gonna be it's gonna look like this. There's a ton of numbers on it, okay? But again, this is one of those things to just let it process for a minute, because if you just glance at it and you go, nope, like, remember, it's okay to not understand, but it's not okay to not try, right? Try to pick up on something that looks familiar. And I think you'll be surprised when you look at the unit circle and you're really looking and trying to pick up on those patterns and those understandings. They're going to be really, you're going to start to see the pattern. There are going to be familiar things, okay? All right, so this is 45 degrees. Now I saw in there that somebody asked, how does pi over 6 equal 30 degrees? So with this unit circle, what is also bringing in is something called radians. So degrees, we have 360 degrees in a circle. All right, all the way around a point, we have 360 degrees. Now we can take that 360 degrees and we can actually use, there's another way to talk about not just the degrees of the, okay, wait. Let me think about how I want to say this. Okay. So 45 degrees measures this angle. But what we can also measure is this distance here. Okay, which is sort of like the arc length. Okay, that's where you get radians from. So radians are, you take the radius of the circle and how many times it fits all the way around the circle. Now what they realized, they meaning like ancient Greeks, right? They realized that you could fit about 6 of the length of the radius all the way around every single circle. It didn't matter how big or how small it was. Right? Now, we have further discovered, and we now call this number about 6, right? We call it 2 pi. So pi is at 3.1415, blah, 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 blah. You can fit that many radii, from your circle around half of it. Okay, so all the way around would be 2 pi. You can fit that radius 2 pi times around the circle. So 2 pi radians is the same thing as 360 degrees. So 30 degrees out of 360 would be whatever out of 2 pi. Okay, now we can go through and we can solve this whole proportion, or I can just tell you, right, that 30 over 360, we can convert this from degrees to radians, and converting from degrees to radians, we use this unit right here that it's 2 pi equals 360. So if I have 30 degrees, I'm going to multiply that by pi over 180. And if I multiply that by pi over 180, because 1 pi is in 180 degrees, because 2 pi is in 360 degrees, right? So I've got 30 pi over 180. 30 over 180 is 1/6, so that is how it becomes pi over 6. So 30 degrees is pi over 6 because pi over 6 is 30 degrees in radians. Because 30 degrees is that fraction of a circle. So 30 degrees out of 360 is pi over 6 over 2 pi. It's just kind of a practice. Oh, where did I get the 30 from? So somebody had just asked in the comments, why is 30 degrees the same thing as pi over 6? So that's just where I got the 30 from. Okay, it was just kind of showing you like how to go from degrees to radians. Okay. So Ben, we're not quite into differential equations on this channel, but if you have a question about it, you can pop it in the chat. There's lots of people that'll be able to help you out with that. Okay, so 45 degrees on the unit circle, or I mean 45 degrees just in general. Okay, so 45 divided by 180, oh, whoops. So 45 divided by 180 is 1/4. So this in radians is pi over 4. Ooh, an extraneous solution, Caroline. So I can quickly tell you what an extraneous solution is, then we'll go back to the unit circle. Extraneous solution is a solution that you can get when you solve it. When you solve an equation, but then when you plug it back in, it doesn't always work. So that comes up a lot with logs and some like polynomials, things like that. If you plug it back in and it doesn't actually solve the equation, it's a solution that just kind of arose by the way you solved it. So it's just an extra solution that doesn't actually work. I know. I hear it. I know. It's a solution that you get when you solve it that doesn't actually solve the equation. This is why people hate math. Oh boy. Okay. So, but if it wasn't 1/4 and it was 2/4, what would it be that? Oh, so if it was, you mean like pi over 4? So if it was 2/4, that would be pi over 2. So then it would be 90 degrees. Negative radians and negative degrees, those can also happen in the unit circle because you're just talking about, it's sort of like you take your angle and you have it in the origin and you're just kind of swinging that arm around. So a negative angle or like a negative radians or negative degrees, it starts from here and it just goes down instead of going up. So a negative degrees, negative radians would go this way, right? They move clockwise instead of counterclockwise. Okay. Okay. So let's see. Okay. So with this, the unit circle, again, if you want to really dive into the unit circle, take a look at one that's online to see the whole complete unit circle, not just my little hand-drawn one, which is beautiful, but it's still just hand-drawn, right? So if I pull this triangle here, this line, this dotted line that goes down back to the x-axis and this x-axis. Okay, I'm going to pull that out and I'm going to look at it here. Okay. So this is 45 degrees, right? We know that this hypotenuse is 1. The reason we know that hypotenuse is 1 is because it's from the unit circle. Now this side length and this side length, okay? When you look at the unit circle, okay, and I'm going to pull up my unit circle. Okay, so when I look at the unit circle, this point here says that it's root 2 over 2, comma, root 2 over 2. Gross. What a gross coordinate point. And what in the world does it mean? This is where it gets so confusing, right? When you're just looking at this unit circle, when you're first given that unit circle and you're going, what is that? Okay? What it is it's based off of a special right triangle. So with a special right triangle, so a 45, 45, 90 triangle, it's a triangle where these angles are both 45 degrees, obviously not to scale. In fact, I'm going to redraw that a little bit because it is way not to scale. Okay. Okay. So 45, 45, and 90. These two angles are congruent, so these two sides are congruent. That's a basic kind of rule in trig and in geometry, right? So you've got this opposite angle that's going to be if the angles are congruent, then the opposite sides are congruent. This side length here, okay, is going to be, let's see, let's call these side lengths out here. Let's just call those A. Okay, now A and A, right? Because we know that they're the same thing because these are 45 degrees, so these sides are the same. Now, the way that this works is it's based off of Pythagorean theorem, right? So I'm going to call this H. Okay, now I'm going to show you guys where these special right triangles got their numbers from. They're not just arbitrary numbers. I know it feels like it. Right, so let's do Pythagorean theorem, and we're just going to do with the letters because we don't have any values other than those 45-degree angles. So I know that a squared plus a squared equals h squared, right? A squared plus a squared, I can add those together to make 2a squared. Okay. Now, if I want to figure out what my h value is. Okay, like what is h? So in order to do that, I've got this is h squared. I can just take the square root of that. And I can also take the square root of this, right? So I'm going to take the square root of both sides. I'm going to rewrite it here. I've got 2a squared equals h squared. I'm just going to rewrite it so we don't get lost. Okay. Square root of h squared is h. Now, since we're in geometry, since we're talking about side lengths, I'm just going to do the positive root. I realize that it should be plus or minus h, whatever, right? But since I'm just talking about this, I don't need to worry about the plus or minus because it's just positive, okay? Square root of 2, I can't simplify that. So it's just square root of 2. Square root of a squared is a. So now I know that my hypotenuse is not just an h, it is a times the square root of 2. So if I have a problem, I'll solve it. Check out the beam on each angle. So this is 4 and this is 4. Okay, right there, this tells me that I know this is a 45, 45, 90 triangle because these two sides are the same. I also know my hypotenuse is 4 root 2. Why do I know that my hypotenuse is 4 root 2? Because these two are A and A. That's a root 2. My A is 4 root 2. That's my hypotenuse. So, going back to this. Where did this root 2 over 2 come from? So how do we get this 2? So this 2 came from adding this a squared together. So a squared plus a squared is 2a squared. Okay. So now, looking at our right triangle again, looking at our special right triangle, okay, now I know that this radius is 1 if I'm looking at my unit circle. I know my radius is 1. Hold on, gotta get a new board. So that means that 1 equals a root 2, right? My hypotenuse is 1. My hypotenuse is a root 2. I'm sorry, my hypotenuse is 1. And, oh yeah, it's also a root 2. Now I want to figure out what my two sides are. Right? So to get a by itself, I would divide both sides by root 2. Now you're probably asking yourself, but Sarah, you said that it's root 2 over 2. It's not 1 over root 2. Well, now there's that silly thing called rationalizing the denominator. And I know it's not favorite thing, teacher hot take, but rationalizing the denominator, you don't have to do it because calculators will do it now. They can calculate this. They can give you a value for this. It used to be where they couldn't do this, right, with slide rules or log books or whatever they were using, right, before we had big, fancy, powerful calculators. So it used to be a rule that you couldn't have a radical in the denominator. And I mean, I guess it still technically is because everybody will count it wrong. I don't count it wrong. But I do still teach my students how to do this, even though I don't necessarily require them to do this. My nose is itching so bad, I'm sorry. I don't necessarily require my students to do this, but I do want them to be aware of it, because then if it doesn't match up with what's on the answer key, then they know that, oh, it's probably because of this. And so for me, with my students, I would say, okay, if you get 1 over root 2, you're good. But the answer key is going to say root 2 over 2. And why is that? Because you can't have a radical in the denominator. So to get rid of that, you rationalize the denominator, which is where you multiply by the root over itself, because this is just the same thing as multiplying by 1. You can always multiply anything by 1. I don't even have to do it on both sides, okay? Because I'm just multiplying it by 1. Now, multiplying it by this version of 1 that helps me is nice. So root 2 times root 2 becomes root 4. I'm going backwards with this, but bear with me. And then root 2 times 1 equals root 2. Root 2 is root 2. Root 4 is 2. I am all over the place with this. So this becomes root 2 over 2. So 1 over root 2 is the same thing as root 2 over 2. I know. So let's go all the way back over here. And I promise you there is a reason for all of this. So not root A, root 2 over 2. Now we're seeing these numbers start to show up. So if we go all the way back to our unit circle, these coordinates for this point here actually give you those lengths. Okay, so nothing ever changes about the coordinate point, right? It's always going to be x comma y, easy peasy, right? In this case, my x is going to be this length here, right? Because it's this length here. Well, I said in this case, but it's in every case. What am I talking about? Okay, so that's my x value. So in this case, this is root 2 over 2, because that's my x value. My y value is here, and it is also here, which is root 2 over 2. So the unit circle will give you those side lengths of the special right triangles. That's kind of what that unit circle is. So a lot of times what you'll use this for is to, it says find the exact value for cosine of pi over 6. So you find where pi over 6 is on the unit circle, and then you look to see what is, so if it's, what did I say, sine? I think I said sine, or I said cosine of pi over 6, right? So cosine of pi over 6, well, let's just do it. We're here. We might as well do it. So let's find cosine of pi over 6. Okay. All right, so cosine of pi over 6. So we need to find pi over 6 on our unit circle. Okay, so from our unit circle, we see that that pi over 6 is 30 degrees. Okay, yes, I draw it basically the same as a 45-degree angle. That's 30 degrees. Okay, I know this is 1. And this point out here, and I'm just looking at the unit circle, so that's root 3 over 2, comma 1/2. Now cosine is my adjacent over my hypotenuse. My adjacent is going to be my x value, which is root 3 over 2. And my hypotenuse is 1. So cosine of pi over 6 is exactly root 3 over 2. I mean, root 3 over 2 over 1, but I don't even need to do that over 1, right? So cosine pi over 6 equals root 3 over 2. And that's just using the unit circle. So this is usually something that you'll see in Algebra 2. Some teachers may introduce it into like Algebra 1 classes, maybe, but it's really if you're talking about trig. Right, so whenever you start talking about trigonometry is usually when the unit circle will kind of start to trickle in, okay? So tangent pi over 6. Okay, so if we were doing tangent of pi over 6, tangent is opposite over adjacent, right? So opposite over adjacent. So my opposite is going to be 1/2. Again, from my unit circle, 1/2 is my y value. So the radical 3 over 2, this is all from the unit circle here. Okay. So this is all from the unit circle. So when we've got, so opposite over adjacent, so this is going to be 1/2. I'm going to have to write it down here. 1/2 over root 3 over 2. If we think about going back to dividing fractions, right? So this is 1/2 times 2 over root 3 because you flip the bottom and you multiply. Okay. So this is going to be so the 2's will cancel out, and I've got 1 over root 3. Now again, this is not in proper notation because any math teacher is going to tell you that you have to rationalize the denominator. You don't have to, but they all require you to. So now to rationalize the denominator, right, we would take 1 over root 3, 1 over root 3, and we would multiply it by root 3 over root 3, which gives us root 3 over 3. Now, if you plug these into your calculator, you're going to get the same decimal because they're the same thing. This is just another version. This is just like a more widely accepted version or form of your answer, I guess I should say. Okay. Now, one thing that is nice, it doesn't really do that. That's okay. All right. So, but what I was saying is that one thing that's really nice is that if you do 1 divided by root 3, and if you do root 3 divided by 3, you're going to end up with the same decimal. So that is a way that you can double check if your teacher is okay not to, that you don't have to, you know, rationalize the denominator and all of that. Okay, we are through trig. So let's see. Let me scroll up a little bit. Okay. Oh, yeah. Let's see. Yep, so the 30 and 60 angles match yep, it's all special right triangles and unit circles. Let's see. So exponent laws. Caroline, we can get into exponent laws. Sure. Okay, so you say solving equations with lots of exponents, but I have a feeling that you mean expressions, not equations. And I know that feels like I'm sort of like mincing words, but it does make a big difference. So let me pull up a practice sheet I just did. So if we have something like 2x squared y cubed times 3xy. So something like that, I'm assuming. Yeah, see, Matt, like I wish that everybody would move away from rationalizing the denominator because you don't really have to do it, but you do because all the answer keys have rationalized the denominators. But yeah, once I have pointed out to my students that like, oh, you just need to like plug it into your calculator, it's a lot easier with the decimal, it's fine. Okay, so yeah, so Caroline, something a bit more like this. All right, so basic exponent rules. So this one shows a lot of the multiplication rules. Now, it helps to remember what the exponent actually means, right? So the exponent, or the power, means how many times you're multiplying the base by itself. So here, I could write this out as being 2 times x times y, right? Cubed. And then this is 3 times x times y, right? Times 3 times x times y. Okay. Now this cubed means that I am multiplying this by itself 3 times. So this is 2x squared times y times 2x squared y times 2x squared y times 3xy here. So if we think about this in expanded form, right? This is the expanded form. Okay, I've got 2 x's. So I've got 2, 4, 6, 7 x's being multiplied by themselves. So I'm going to go ahead and I'm going to write that down. I've got x to the 7th. All right, now the numbers, let's do 2 times 2 times 2 times 3. So 2, that's 4, 8, 24. So 24x to the 7th, and then how many y's? 1, 2, 3, 4. So y to the 4th. So this would be my simplified version of this expression. Okay, hold on, let me do the little puzzle piece. Okay. So the rules, right, are that you would, if you're multiplying these things together like this, you add the exponents. Okay, but if it's a power of a if it's a power of a power, you would. Oh no, now I'm second guessing what I thought. Okay, let me start over because I think I said it right, but I want to make sure. If I'm just multiplying these together, I would add the exponents or add the powers, right? I would add those exponents, so it would be 2 plus 4 plus 2 is 6, right? Here, if I've got a power of a power, I would multiply these together. Okay, so I would multiply these together if it's in the parentheses. Now this power only has to do with this. Okay, this becomes 2 to the 3rd, x squared to the 3rd, y to the 3rd. Okay, now it can get really confusing. If you don't fully understand like what's going on with like the expanded form and the condensed form and exponential form and all of that. But it can also get really tricky when you're talking about division. Okay, so when you're talking about dividing exponents, if I have like 4b to the 4th c squared over 2b squared c to the 3rd. Now, exponent rules are where you just subtract them. But where does it come from? Why do we just subtract them? Let's get into that. So we have 4 over 2 times, I'm just going to kind of split them out. Then I've got 4b's multiplied on top, and then 2b's multiplied on bottom, and then times 2c's on top and 3c's on the bottom. Do I expect you to write this out every single time? No, please don't write this all the way out, but you can start out by doing that. So then you're ready to just kind of be able to visualize it. This is why I always start out with my students having them write it out in the expanded form, just for like enough problems to where you like get it, like where you can start visualizing it in your head. Because if you can't really visualize what's going on, you may get tripped up if something doesn't look totally familiar, right? So here, 4 over 2 becomes 2, right? B times B times B times B over B times B. These 2b's multiplied together and these 2b's multiplied together, they're the same thing. They're going to cancel out. So now I'm left with B times B on top. C times C, C times C. Those are going to cancel out. So all I'm left with is a C down at the bottom. So now I've got 2 times B over C, and that becomes 2b squared over C. So again, I could do 4 over 2, and that's going to be 2. I could do b to the 4th over b squared. That's 4 minus 2 gives me 2. 2 minus 3 gives me -1, which brings us into negative exponents. So that means that a negative exponent, all that the negative does is it flips it into the reciprocal, okay? So if I've got if I've got 2a to the -2 b cubed and c. Yeah, let's just leave it at that for now. Oh my God, my nose is so itchy. Okay. So there's no simplification that we can do, but usually when you're doing these like simplifying expressions, they'll say to like leave them all with positive exponents. So this one is a problem, right? This one is a problem, this a to the -2. But remember that negative, all it does, so a to the -2 power, the negative on it just flips it. So if the negative were on the bottom, it would flip it to the top. So this is going to become 1 over a squared. So once I flip it, the negative gets dropped. So this one becomes just, this a squared is going to go down to the bottom. So this is going to become 2b cubed c over a squared. And that's how you would write it with no negative exponents. It would just be all positive exponents. Again, if you had a negative exponent in the bottom, if I had 4ab squared c over 2a -2b. Ooh, this is a fun one. bc, actually, let's do that. All right, so let's think about what this would simplify down to. We've got 2a. So we do know that the 4 over 2 is just going to become 2, right? We know that that's going to be a 2 on top. Now I'm going to write all my in-between steps, right? I've got my original a on top, and then this a to the negative 2. Actually, hold on, I'm going to kind of space this out. So this a to the negative 2, that's going to pop up to the top and stay as an a squared. So this actually becomes a cubed. Okay, because nothing happens to this a. And this a to the negative 2, it's going to pop up and it's an a squared. And a times a squared is a cubed. B squared over b. This is gonna cancel out one of these, so I'm left with just b. And then the c's cancel out, so that's it. That's it. Okay, good job, guys. So fractional exponents, so kind of like negative exponents, once you realize what they do, they're not so scary. But when you first see them, you're like, oh my God, why are there fractions up there, right? So with a fractional exponent, or what we call a rational exponent, if I have a to the 1/3 power, all that is, it means it's the cube root of a. So the denominator in the fraction exponent becomes the root. The numerator becomes the power. So if I have b to the 2/5 power, so that's going to be the 5th root of b squared. And other than that, these behave just like regular exponents, right? If you multiply them together, you're going to add, you're going to subtract, all of those exponent rules still apply even though they're fractions. Okay. So yeah, fractional exponents are once you kind of get over what they are, like the initial shock of seeing them, that's what they are. Is the denominator is the root and the numerator is the power. Okay, so grade level is, every grade level, you really start dealing with these in Algebra 1. Usually you'll start to see some radicals and simplifying radicals and things like that. The rational exponents, definitely Algebra 2. Definitely that's when they start showing up. All right, guys, it is after 9, so it is my bedtime. But keep tuning in even all through the summer. We'll still be joining you for Math Thursdays as consistently as possible. But if you are worried about a summer slump, you're worried about a summer slide, maybe you want to just brush up on some of your algebra skills and your pre-algebra skills before moving into your next level of math, come join me in my Algebra 1 boot camp. That's going to be through July and August. And June, July, August?
Last week of June.
Last week of June.
For 8
through
weeks.
8 weeks. So 8 weeks it's going to be going on. So we're going to go through a lot of pre-algebra things. We're going to start previewing some algebra things, and it's going to be fun and a great way to spend your summer. So click the link and do the stuff. Check it out. Let me know what you think. If you have any questions, comments, concerns, anything like that, reach out, send me a message, and have a great night. Bye.